lecture we saw the Chebotarev density theorem, we saw the Brouwer-Nesbit theorem, and we saw what almost looked like a counterexample to the Brouwer-Nesbit theorem, two completely non-isomorphic representations with totally different kernels that seem to have the same trace. But you can't apply Brouwer-Nesbit because they're going to GLN of different fields. You see, that would kind of be cool, right? If they both took values actually in GLN of Q, instead of GLN of QL, then you would be able to use Brouwer-Nesbit for Q. But the problem is these cyclotomic characters don't take values in GL1 of Q. In fact, in some sense, that's actually a proof, right? If they were both taking values in GL1 of Q, then you would be able to use Brouwer-Nesbit. Maybe you wouldn't. No, because the topologies are still different. No, I don't know. Life's difficult. Where am I up to? Oh yeah, so there we go. So hopefully I've given you just enough to get confused, and then you can think about it later and get unconfused. I'll give you another weird example of this phenomenon. Right, another weird example. If you know about elliptic curves, let's have K some number field. K is the rationals is fine, right? I don't know. Typically in some first course on elliptic curves, if it's lectured by somebody old school like Castles, then you do everything over Q. And then you just mumble that it generalizes to number fields. I don't know how it's taught nowadays, but I was taught old school. So E of a K an elliptic curve. And then we could have P a prime number. So elliptic curves, there's some discriminant involved there as well, right? S is some finite set of finite places. Well, let's call it S0, because when I take the Tate module, there's going to be an extra bad prime. Finite set of finite places of K. That's just a stupid way of saying maximal ideals of OK. Right? Primes of K. So let's take some elliptic curve. I haven't really talked about elliptic curves, so don't worry too much. This is just another example. So if you don't know anything about elliptic curves, don't worry. So let's let S0 be the finite set of finite places of K where E has bad reduction. And that reminds me. Talking of bad reduction of abelian varieties, 4 till 5 today, you have three choices. You can either do what you like, or you can listen to me doing review, where I'm going to talk more about number fields and Frobenius elements for those that haven't seen it before. Or you have at least one other option, which is Rebecca is going to talk about Neron-Ogshafferovich. Rebecca will talk about Tate modules of abelian varieties at 4 p.m. So if you know everything about Frobenius elements, then you might want to go to an informal talk. And if you've never seen Frobenius elements before, you might want to come to my review. And if you've got other things to do, you might well go to other things. But the reason I'm mentioning this now is because we have to decide where these things are happening. So this obviously doesn't represent a commitment, because I'm sorry to pest you, but this is just purely for numbers. Can I get some show of hands? Who is likely to come and listen to me talking about Frobenius elements in review? 1, 2, 3, 4, 5, 6, 7, 8, sort of 10, 11. Who is likely to want to see Rebecca talking about the Neron-Ogshafferovich criterion? Now that looks to me like more people, which is great. So what's the answer? Is Rebecca in? Rebecca's in here? Yes, of course it's fine. So where do I do review? Right. I'll be in the common room upstairs doing review 4 till 5. That's a really good place to review, actually. I kind of like that idea. So there we go. So let's let E be an elliptic curve. Then E has got good reduction away from some finite set of places. And we could look at its Tate module. If L is some prime number, right, you can look at E of, as I say, if you don't know anything about elliptic curves, then don't worry. Then the L to the n torsion points will have an action of gal k bar over k. Well, gal k bar over k, right? And therefore take the limit over all n, and I get gal k bar over k to a group which is non-canonically isomorphic to GL2 of ZL. I mean, defined up to conjugation, right? At some point, I had to choose a basis of a free rank 2 ZL module. So this is not quite, this is, I mean, right, well defined. Up to conjugation. But I mean, that's life, right? Everything's only defined up to conjugation. The Gower group's only defined up to conjugation. So there's some limit, and that's called the Tate module of E, right? Okay, and here's a general fact that you can read about in Silverman, is that if P is not in S, and also P doesn't divide L, right? So S is not quite right, it's S0. That's why I call it S0. If P is not in S0, so P is a prime downstairs, P is a prime of K. If it's not in this bad set and it doesn't divide L, then this thing is unramified, right? I need notation, don't I? Let's call it rho of EL. Then indeed rho of EL factors through. Well, sorry, I'm a step ahead of myself. So here's just a fact: is that rho of EL factors through gal K, and I want to put S. But what's S? I've got to be careful, because where does this representation ramify? It's just like the cyclotomic character. There are problems at S. Of course, there's problems at S0. But the L-adic Tate module, the determinant of the Tate module is the cyclotomic character, which we just saw is kind of infinitely ramified at all primes above L. So this is S0 union the primes dividing L over K. Right? So because I'm just telling you that this thing factors through this Galois group, that means I can make sense of rho EL of frob P. And I can't even, that's some conjugacy class of matrices. So I can look at the char poly of this, and that's finally a well-defined object, and it just turns out to be x squared minus APX plus the norm of P. So if you're thinking about K as Q, this is just curly P is a prime number P, and that's just P again, right? Where AP turns out to be is 1 plus the norm of P minus the number of solutions, right? The number of points on that residue field. So my point is that at some point I chose some prime L, right? Just here, I chose a prime number L. And I chose my prime number L, and I got a representation that somehow depends on L. It's an L-adic representation. But when you look at this Frobenius element, that doesn't depend on L anymore, right? This AP is just some random integer. This is an integer. This characteristic polynomial, if you think about it, is in Z, right? Well, let's stress the fact that it's in Q. It's in Q of X, which happens to live in QL of X. And in QL of X, that's where the calculation occurs, because this is an L-adic representation. So just the same as the cyclokinetic character, just the same as the cyclotomic character. I broke for a little bit there, but I'm fixed now. The cyclotomic character is just the same. You choose a prime L, you get an L-adic cyclotomic character, and then the trace of rho of frob R was equal to R, and that was somehow independent of L. So it's a very strange phenomenon. right? But so in particular, the trace of so I want to say that the trace of rho EL from P is, in particular, is AP, right? Independent of P. Sorry, independent of L, right? But this is independent of L in some very weird sense, right? Because the trace is an element of QL, but the answer turns out to be independent of L because there's some weird coincidence because there's this field called Q which kind of lives in the QL for all L. So this is a subtle thing, right? But rho EL is not isomorphic to rho E M P R. I just don't P if L isn't P, right? Because this one here, this is infinitely ramified. This is infinitely ramified at L. Right? This is really badly ramified at L. It's got wild inertia subgroups and everything. Wild inertia, horrible. It's a huge thing, right? And this is very, very. The ramification here at some random prime L will be much better behaved, right? Much better behaved. At L. E.g., the image of wild inertia will be finite, right? Rho E comma P, whatever I called it, of wild inertia. Of wild inertia at L is going to be finite. And in particular, we're in some situation here where we could maybe use local Langlands, but not here. So this is a really subtle phenomenon. So I think I'm at the stage now where I can write down a formal definition. Yeah. So these are supposed to be slightly unnerving examples. So here we go then. So L-adic representations. Go. Uh-huh. Yeah. These are numbers. This is the number of points, the number of solutions to an equation.
But I thought curly P was a prime of OK.
Yeah, it is.
Oh, we're just assuming a K is Q.
No. It's all there. This means the norm of P. If you let K be Q, that's absolutely fine. But the remark is this turns out to work over any K. And the characteristic polynomial is still in Q of X. Yeah, so in fact, we're going to see this is going to happen, right? We're going to see this in general. We're going to have number fields on the left-hand side, which is where the Galois theory is going on, and we're going to have number fields on the right-hand side, which is the field over which all the traces seem to be living in. And they're different number fields. And your question is perhaps a flag that I should really stress this. There's going to be fields which, listen, this is covered by my notation. There are fields which are called K and L and stuff like that, and there are fields which are called E and E0 and stuff like that. And you can tell which is which because the K's are on the left-hand side and the E's are on the right-hand side. And I'm going to use E consistently and E0 to mean right-hand side stuff. Forget about the elliptic curve. That's an errant use of E, which you won't be seeing again. So L-adic representations. So here's the setup then. K is a number field. And now I've got E. E is not an elliptic curve now. E is a finite extension. E is a finite extension of QL. Right? And E equals QL is fine. E equals QL is already, if you K equals Q is fine. If you're trying to see examples in your head, then you don't have to work in this generality, but all the complexities already exist in this case here. This is not like some story about factoring ideals into prime ideals, where you can pretend that K is the rationals, and then it turns out you've lost all of the subtleties because you don't see class groups and blah, blah, blah. It's absolutely fine to live in the most basic possible case here. Because the subtleties are still immense. So S is some finite set of maximal ideals of OK So a finite set of finite places of k, I sometimes call it. And then we've got rho gal k bar over k. So here's the definition, right? If rho gal k bar over k to g l n of e, sorry, this is not gal k, I'm going to put s, right? There. If rho from gal ks over k to g l n of e is continuous with respect to the Galois profinite topology on the left-hand side, is the continuous with respect to the obvious topology on the left-hand side and the L-adic topology on the right-hand side, right? On the right-hand side. And profinite topology on the left, right? So these are complicated topological groups, and there's a continuous map, and thinking about that, I don't know, might make your head hurt. But if I've got that situation, we call L an L-adic representation. We call rho an L-adic representation. Of gal k bar over k. Okay, so maybe just the remark is that for convenience, I have built in I've built in a condition here, right? This is not a representation. Gal k. It's a representation of another group. What am I talking about? This is a representation of gal ks over k. But that is a representation of gal k bar over k, because gal k bar over k surjects onto gal ks over k, and that goes there. So I'm somehow implicitly demanding that rho is unramified outside S. And in particular, I'm demanding an L-adic, so equivalently, an L-adic representation of this guy is a representation of this guy to here that's unramified outside a finite set of primes. So, I mean, other people might say different things, because it turns out that there do exist examples of L-adic representation, of continuous maps from here to here, which are ramified at infinitely many primes. Right? Those abstractly do exist, but they can't be number theoretic, right? Because in number theory, everything is unramified outside a finite set of primes. I mean, you can be ramified, you can take something like some perfectoid field, that's like humongously ramified at one prime, but that's a local object, right? Ramification can be as crazy as you like, but when you're doing global objects, the natural global objects that I've seen are unramified outside finite sets of primes. And things like gal q bar over q, which are not unramified outside a finite set of primes, do you ever really study it? I don't know, you just study images of it, which are unramified outside a finite set. So there's an L-adic representation. So now here's some definitions, right? So, or we say, we also say, that rho is unramified outside S, right? Yeah. So now I need some definitions, you see. So now here's this weird thing, right? We say rho is rational over E0, right? Where E0 is a subfield of E, where E0 is a subfield of E, and now what you should be thinking is that E is some finite extension of QL. Presumably I said that at some point. Did I say that at some point? Yeah. Great. I can't see it on the board. I really want to have said it somewhere. I said it, but I didn't write it. So E is a finite extension of QL. Sorry, that should have been in there. Nothing. Okay. Oh, I've done a dumb thing? Aha. Sorry, I'll go over here. We say rho's rational over E0. So E is a finite extension of QL, but E0 is supposed to be a number field. That's what's happening here. E0 is going to be Q in this example of an elliptic curve. So what does it mean to be rational over E0? It simply means if for all primes P not in S, the char poly of rho of frob P, that's a well-defined polynomial. in E of x, right? But it actually lies in E0 of x. So that makes sense. Because this clearly, by definition, that's going to be in E of x. So I'm just demanding that all the coefficients live in a subfield. Remember, you've got some random representation to GLN of E. If you take some random element, then its char poly will just have coefficients, some random elements of E, right? Random numbers in, take some random element in that Galois group. The char poly of rho of that element will be some random polynomial with coefficients, random elements of E. But if I take these special Frobenius elements, then by some weird coincidence, they might all live in E0. So there we go. There's some random thing. Okay, maybe I'll do it, e.g., if rho is kind of this cyclotomic character, right, the cyclotomic character, then rho, that goes from gal q bar over q to GL1 of QL, right? But rho of frob R is equal to R, and therefore, this is for all R not equal to L, and therefore rho is rational over Q. So it really does happen, right? Take module elliptic curve, take module of elliptic curve, rational over Q. Where do Galois representations come from? Well, we've got the cyclotomic character and we've got the Tate module elliptic curve. And then the next step after that is L-adic cohomology of a smooth projective algebraic variety, obviously. So let's do that one next. Rho equals hi of x over q bar, well, over k bar ql. The L-adic et al. Cohomology of an algebraic variety, of a smooth proper algebraic variety. Who knows what that means? Brian does. Hi, Brian. I don't know what it is. I mean, I sort of know what it is. There you go. There's a perfectly good example of an L-adic Galois representation. Yeah, that's rational as well. It's rational over a number field. Well, it's rational over a number field, yeah. Must be that. Must be rational over. I'm confused now. Should I be confused? This must be. You see, I'm talking about things I don't know, Brian. Help! I need help. Can you text me? I'm going to say this is rational over Q. So what's? I was going to say it's rational over a number field, but how can it possibly be rational over a number field if that number field isn't Q? This must be rational over Q. Rational over Q, I think. I think this must be a famous theorem of Deligne. This is perhaps a famous theorem of Deligne. Or I might just be wrong. I think that's what's going on. I could just lie and kind of tell you that this was definitely all true, but then I might end up with egg on my face later. Yeah, there's these things called the Weil conjectures. It must be something to do with them. Oh yeah, what do the Weil conjectures say? There. Yeah. It's the kind of thing that if I think about this carefully, I should be able to work it out. But I don't really want to. I've written rational over a number field on my notes. That's just can't be. That's. Yeah. Right, but you see, they can't be rational over some random number field E. Because E has to live in QL for this to make sense. The char poly, this is the point, right? The char poly, if I let L vary, that char poly needs to be independent of L. This must be right. This must be right. This is a well-known, famous theorem of Deligne, right? There's some other crazy notion as well. Here's more definition. Here's another definition that I don't think we'll particularly use. Rho is pure of weight W. The only reason I meant, as is perfectly clear, I know essentially nothing about Étale cohomology, the one thing I know about, the one thing you need to know about Étale cohomology is it's a source of L-adic Gauss representations, and it's, in some sense, it's the only source of L-adic Gauss representation. All these other things are special cases. Right, kind of H2 of the projective one space. I think that's the cycle. It's probably the inverse of the cyclotomic character. And H1 of an elliptic curve is the dual of the Tate module. All these examples are all just, this is just some completely subsumed by some theory. In fact, the only L-adic Gauss representations we know are either Étale cohomology of an algebraic variety, possibly with some fancy coefficient sheaves, or somehow continuous deformations of such a thing. Those are like the only, I think those are the only examples of L-adic Gauss representations that exist. So another definition, rho is pure of weight W. This is just kind of a cool thing. This is, well, I'll tell you what it is. If rho is rational over some number field, E0, so that means rho 0 of frob P has got coefficients, the char poly's got coefficients in E0. And furthermore, and for all field maps I from E0 into C, well, I better go from E but actually. So rho is rational over some number field E0, which means that the roots of the char polys, so let me just remind you what that means. That means rho of frob curly P is going to be an E0 of X, right? So rho of frob P is some polynomial. The coefficients are all in E0. It doesn't mean the roots are in E0, of course. So we're better, I want to talk about roots, so I better have a map from E0 bar into the complexes, some field injection, and for all eigenvalues alpha, so whatever, eigenvalues alpha of rho of frob P. So of course this is P, whatever, this is P not in S, of course, right? For all eigenvalues alpha of rho frob P, I can tell you what the size of that eigenvalue is. I can look at I of alpha, right? And that's now a complex number, and that's got to have size. It's QP to the minus W over 2. Oh, there's a sign issue. Do I do... Some authors might call this pure of weight negative W. I think I'm covered now, if I just say that. Yeah, so QP is the size of the residue field, right? Is the size of OK mod P. So if you're doing K is the rational numbers and then P is a normal prime number, then QP is just P. There you go. And I think maybe for technical reasons, one might want to define pure of weight W without this hypothesis that rho is rational over a number field. And then you get this kind of stupid situation where rho of frob P is in E of X, and you could look at kind of completely discontinuous crazy maps from E bar into C, and you could still demand this, right? What I'm saying is, if you don't demand it's rational over E0, you could just work with all of E, and then I would be a rather pathological object. And the conclusion will still be the same. But if you have something that's abstractly pure of weight W in that sense, then when you think about it, these eigenvalues had better not be random random p-adic numbers, because if you've got a random p-adic number that's not algebraic over q bar, then it's going to go to a random thing. So I think you can define pure of weight W by not demanding it's rational over some number field, and then kind of proving that a posteriori, that if you're that if you're pure of weight W, then you must actually be rational over some algebraic number field anyway. There's some, as I say, I've not read the proofs, but somehow it wouldn't surprise me if this sort of thing actually shows up in them in some sense, because you do clever comparisons of Étale cohomology with, I don't know. I should say, the less I say about Étale cohomology, the better, I think. There's pure of weight W. So in fact, Deligne proved this as well, right? Deligne proved. Let me just, I want the cyclotomic character to be pure of weight -2. Yeah, that sounds right, doesn't it? So I've gone, this frob p is an arithmetic Frobenius. The cyclotomic character sends rho of frob p to p. And so that would be p. And so negative W over 2 has to be 1, which means W is -2. So the cyclotomic character seems to be pure of weight -2, and I think that's right. So with the notes, yeah, great, this is good. So Deligne says that at hi of xk bar comma ql is pure of weight I for x smooth projective, well, x smooth proper. So there you go. I think I've finally, I think I finally sorted everything out. I don't know why I'm going on about Étale cohomology. We're never going to see it, really. Right, example, cyclotomic character. We've done that, yeah, I guess. So example. Did we do cyclotomic character being rational over Q? We did tape modular elliptic curve rational over Q. Yeah, cyclotomic character rational over Q. So it turns out that cyclotomic character is pure of weight -2. And I'm kind of happy with that, because the only thing I know about Étale cohomology is that H2 of P1 is the cyclotomic character inverse. It's inverse because cyclotomic character's got something to do with homology, not cohomology. So there we go. Here's an interesting thing. Tape module on an elliptic curve. There, that's pure of weight -1. So what does that actually mean? This says the roots of x squared minus apx plus the norm of p are complex conjugates. Rather than being real unrelated numbers. And so that's if and only if AP is at most 2 root the norm of P. And that's some famous thing, right? Maybe if you've seen elliptic curves, then you've seen, this is from the 30s, what's it called, the Hasse bound or something, for the number of points. This says AP is related to the number of points on the elliptic curve. So this says something like the number of points on an elliptic curve is 1 plus p minus a small number, and the smallness of the number is exactly the condition that makes the discriminant of this polynomial less than or equal to 0, b squared minus 4ac, which is exactly the condition that forces the roots to have norm, for this to be pure. This is a very weird way of reinterpreting this result here. So there's kind of a cool thing. Blah, 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 comparable sequences. Ooh. Yeah, now, okay, so now things are going to get deeper. Right. So that's analytic. So now L's going to vary. Okay, because I want to talk about the example of the, I've been banging on about the L-adic cyclotomic character for different primes L. Kind of looks like the traces are the same, but the representations are different. So now I want to formalize this, right? I'm going to formalize that whole notion that cyclotomic characters are definitely not the same, but some have the same traces. So the setup now, you have K a number field, K's Q is fine, S0, it's a finite set of places, So this S0 is just like S. We're going to have an S later, it won't be S0. Basically, the point is that the L-adic cyclotomic character is really, really badly ramified at L, but I don't want to put L into some... If I put L in S and then I let L vary, I've just put every prime into S. So that's not very good. So I'm going to have an S0, and then my S will be S0 union L, basically. So there's some S0, finite set of finite places. And now let's say we're given the following. Let's say also we're given the following huge amount of data. So we're also given the following data. For all P not in S0, I'll give you a poly. Shall I call it V? Is now a good time to start calling it V? Maybe not. Let's not do that. For all P not in S0, a polynomial, let's call it FP. Okay, I'm totally diverging from my notes here. So if in 2 minutes' time I've started writing Q's and V's on the board that don't have a definition, then yell at me. There's a polynomial FPX. You should never it's the rule 1 of lecturing, never deviate from your notes. I just never adhere to that rule. I get into terrible... So this polynomial, where the heck is this polynomial? You see, I've deviated from my notes. This polynomial has nowhere to live. This is going to have to live in E0 of x, right? Where E0 is a number field, which should have been mentioned beforehand. So E0 is some fixed number field. Let's just pretend I said that already. And now for all primes P not in S0, I've got some polynomial. I've probably got an example of one somewhere. Yeah, there's a great example, right? P is a prime of good reduction. E0 is going to be the rational numbers, and there's a polynomial. Another great example would be Fp of x could just be x minus the norm of P, or x minus P, if you're pretending that E0 is Q, that K is Q. So here we go, and now what I want to talk about is a collection of infinitely many Galois representations as L varies, right? This is a really fundamental object, and that I'm ploughing through this really carefully because these are fundamental objects that we have to understand, and we'll just talk about them more in review today. Right. So now here's the crazy thing then. Now let's say also that for all primes of E0, right? For all primes, finite places, whatever. For all maximal ideals, lambda living in the integers of E0, right? So if E0 is Q, which is fine, then I'm taking a prime number. For all maximal ideals lambda of E0, we have an L-adic representation. So you see I've got so I can complete E0 at lambda, right? There. That's some finite extension of QL, where lambda divides L, right? This prime ideal of the integers of this number field, that will contain a prime number, L. So let's say that for all maximal ideals we've got an L-adic representation, so that would be called rho lambda there, and it's going to go from gal, well, K, where's this well, I've got this S0, so I'm going to put S0 up here. This gal representation is maybe going to be ramified at S0, but I also want to allow it to be ramified at all the primes dividing L. So this is union the P dividing L over K. I've got a representation from this Galois group here, there, to GLN of, let's complete, right, E0 lambda. There, I'll take the algebraic closure, why not? Let's say I've got one of those. So there's the setup. K is a number field, I've got a finite set. This is not part of the story. So I'm just checking everything's there. We've got a number field, we've got a finite set of finite places. We've got another number field, E0, not to be confused with K. And I've got a random polynomial with coefficients in E0. And now we've got L-adic representations for all, right. I mean, the simplest thing to there's no harm in thinking E0 is Q. Think about E0 is Q, then what I'm saying is for each prime number L, I have a representation to GLN of QL attached, this row lambda. And now the miracle then is that, so we say that this row L, that row lambda is a compatible system of L-adic representations, or perhaps of lambda-adic representations, if you like. There, so that I've just defined a compatible system of L-adic representations if, where's the compatibility? See, I haven't said anything yet. All I've done is all I've said is that we have got certain objects. I haven't written any relationship between any of these things. But of course, you know what the relationship's going to be. If the char poly, if for all lambda and for all p, not in S0 and not in, and for all p not in S0 such that p doesn't divide lambda, there, so lambda divides L. For all p not in S0 such that p doesn't divide L, rho lambda is unramified outside. Rho lambda is unramified at p, that's part of the definition. So rho lambda of frob p, there, has char poly. I should have a char poly somewhere. Here we are, fpx. Right? And so the miracle is this is independent of lambda. That's the weird thing. So I've got all these L-adic representations for lots and lots of different primes L, and they're all independent of lambda. So let me tell you something which I believe is unknown, actually. So there's a compatible system of L-adic representations. And so that basically says they might not be isomorphic, but their traces agree in some weird way. So I finally finished the definition. So examples, kind of cyclotomic character, right? Fp of x is just x minus p. Right, take modular elliptic curve. The cyclotomic, it's cyclotomic characters now, right? Because we're considering them all of them. Take modular elliptic curve for all L. We get E0 is Q, and Fp of x, whatever, is x squared minus AP plus norm of P. That's just, if K is Q as well, this just says x squared minus APX plus, sorry, there's an x. An étale cohomology. That's also known to be, I think that's true. This is known to be a compatible sequence, known to be a compatible system. So while I'm here, like Deligne didn't prove everything. Let me show you something that Deligne can't prove. Here's kind of a cool generalization. is that instead of just asking that these traces are the same, you can use local Langlands. Use local Langlands. Right? And you could say these rho lambda is above, are strongly compatible So what a strongly compatible means, what I've said here is, do you remember there's a bad, it's gone now, but yeah, it's gone. There was a finite set S0 of kind of primes at which we said nothing. So, for example, with the elliptic curve case and for the étale cohomology case, this S0 is the primes where your variety has got bad reduction. But if you use local Langlands, you could even make sense of what it means for two different, possibly completely ramified representations to be the same. So you could say they have the same Langlands parameter, right? You could say rho lambda above are strongly compatible if what would you do for all p, even in S0, right? And for all, so let's say p divides p, right? For all lambda of E0 with lambda not dividing p, we could look at rho lambda and we could restrict it to gal kp bar over kp, and now we've got an L-adic representation of a p-adic Galois group, right? So now by Grothendieck we get a Wedelin representation, right? And then by local Langlands we get some pi, pi some representation of GLN or whatever of Kp on some huge infinite dimensional vector space. And what we could do is we could ask that depends only on lambda, right? We could even ask, and this turns out to be a really fancy generalization of a compatible system. If you do this fancy story and you understand the unramified local Langlands correspondence, two unramified pi's are the same if and only if they have the same Satake parameters, which is semi-simple conjugacy classes. Anyway, I don't want to get too much into this. They're strongly compatible. If have I done it wrong? Yeah, this could be crazy. Yeah, this can be wildly ramified. So I can look at this wildly ramified representation, but by Grothendieck I get a Wedelin representation, and by Langlands I get a representation of this guy here. So what is this pi really? This pi is kind of pi. What does it depend on? You know, it depends on rho lambda and on p, right? Yeah, lambda doesn't divide p, right? P divides p, lambda doesn't divide p, right? So you can ask, so they're strongly compatible. If this machinery, if this pi is independent of lambda, right? That turns out to be the, you know, that's the strongest question you could ask. So I'd bet this is unknown for étale cohomology. Of smooth projective varieties. So basically what I'm saying is when you take something, let me explain what's going on for Tate modular elliptic curve. Your Tate modular elliptic curve, that's ramified at some finite set of primes where the curve's got bad reduction. It's unramified everywhere else, right? Compatible family, let L vary, we get a compatible family because what I'm saying is take some random p that isn't equal to L, then frob p has some characteristic polynomial that's independent of L, right? But now let's take some prime p where this curve's got bad reduction. Then I know by, you know, what Rebecca's going to talk about is that this Tate module is going to be ramified. So for each prime L, I get a ramified representation of gal qp bar over qp. And can I make sense of the notion of these things are the same? And the answer is I can, because I can use this machinery. And so you can ask, so we won't be using strongly compatible systems, but there's you know. Huh? Yeah, it might have something to do with that. I mean, that would be, if you could prove that, then you would, you've probably proved something like the ends are the same here or something. Where's Illa? I guess she knows a lot about this stuff. Yeah, doesn't the weight monodromy conjecture? Oh, no, but the weight monodromy, yeah, no, that's exactly what the weight monodromy conjecture is about, isn't it? It's about when you have a variety with bad reduction. Yeah, this is certainly going to be related. Because the weight monodromy conjecture gives you, remember this Wedelin representation's got a rho 0 and an n, right? And in the bad reduction case, that's exactly when you might expect the n to be non-zero. And then the weight monodromy conjecture might give you a conjecture about what n should be. But you see, maybe it would somehow depend on L. I don't know. This is harder stuff. We don't need to worry about it. I should get back to my notes, because I'm supposed to be giving a course. Global class field theory. Oh, great. What's the time? What time do I stop? 12:15. Right. Let's get the Adels over with. So that's all I have to say about families of L-adic representations. So right, I'm somehow mimicking what I did in the local field case, right? We've got a number field, and now we're looking at n-dimensional representations of the number field. But now let's now kind of say what we can say about one-dimensional representations. So global class field theory. So like in the local case, I'm going to try and tell you everything you need to know. But I think it would be a little... so this is i.e. what is gal k bar over k ab, right? And again, the reason that this is a tangible question is because for random Galois groups, we can't expect to get hold of elements. We can only expect to get hold of conjugacy classes. But when you abelianize these things, conjugacy classes become elements via the monad construction. And so you get, so there's a kind of a chance that we can actually write down there's a chance that we might be able to write down what this group is. So the answer involves Adels. So I need to say what the Adels are. I think that's probably a good way of spending the last 15 minutes of the lecture. So these kind of look quite unwieldy and scary. And there's an infinite part as well. So let me do the infinite part first. First let me tell you about infinite. I've been using the word finite places without even ever properly defining it. So let's talk about infinite places. K. So K is a number field, right, of degree D over Q. Okay, so K over D. K over Q is D. So sometimes, this is one of the places where if you stick to Q, then you might miss some subtleties. So here, maybe you want to really consider K as a random. You know, you want to do Q root 2 or something. You want to expand your horizons beyond Q for Adels. So an infinite place, so there's some standard fact, if I've got degree D over Q, I mean, it's a number field, right? So it's generated by one element alpha, where alpha, the min poly of alpha has got degree D, and that min poly has got D complex roots, right? So there are D field, there are D field embeddings from K into the complexes there, and I'm going to call them sigma. And I'm going to put a weird little equivalence relation on these. So they're of two kinds. So I want to think, here's the point, I want to think of a map from K into the complexes as giving a norm on K, right? Each map from K into the complexes has got the usual norm on, the norm that you learnt, you know, when you were at school somehow. The norm of Z is root of x squared plus y squared. So it's got a perfectly sensible notion of size on it. And so if I've got some random abstract number field K, the moment I embed it into the complexes, I get some norm on K. Just the norm of some element kappa of K is just the norm of sigma of kappa. Okay? And so it looks to me, at first glance, it looks like we now have D norms. But there's a stupid catch. They're of two kinds, right? And the reason I want to separate these two kinds out, so the firstly is that the image of K, the image of sigma, so that's just sigma of K, actually is a subfield of R. Okay, that can happen. So let's say R1. This is the traditional notation. Well, I let R1 be the number of such K, such sigma. Okay, and then the second kind is that the image of sigma doesn't live in R. And in that case, then C composed with sigma is another field embedding. It's another different field embedding from K to the complexes. Right? So here's C. C is complex conjugation. Okay? So we've got D field embeddings from a number field into the complexes. If you've ever learnt general facts about unit groups, you'll have seen these constructions already, I guess. When you want to analyze the unit group of a number field, you tend to embed it into some real vector space using exactly these sigmas. And you see this phenomenon there. You kind of don't want to use sigma and sigma. Sigma and C sigma are the same. You see that they're the same norms, you see. That's the problem. So I want to consider, so for these bad ones, these bad ones come in pairs, that's the point. So the upshot is that maybe I should call this, is the number of real embeddings, let's call it that, right? That's a good name for it, the number of real embeddings, because it literally is the number of field homomorphisms from K into the real numbers. So the upshot is the non-real embeddings, the non-real sigmas come in pairs, and sigma and C sigma, right? So sigma and the reason that we should consider identifying these things, sigma and C sigma induce the same norm, right? On K, you see, because the norm of Z equals the norm of Z bar. So there might be different field homomorphisms, but they give the same norm. And you see, you think about these primes as giving norms. So the non-real sigmas come in pairs. Let's say there are. So I want some notation for the number of non-real maps. And you kind of would think, I've called that one R1, let's call this R2. But because they come in pairs, I'll call it 2R2, right? Let's say they're 2R2 such maps. Okay, so what we know is that R1 plus 2R2, that's the total number of sigmas. Total number of sigmas. And so that's D. There. But that's the only relationship between R1 and R2, right? It's not like R1 is always 0 or something is always something. So and if you want to see an example with R1 and R2, so e.g. K is cube root of 2. What is R1 and R2? Blah, 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 blah. Blah, 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 blah. Blah, 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 blah. So there we go, an infinite place. An infinite place of K there are two different kinds of infinite places. Is either a real place, so there, V, that's just equal to sigma from K into the reals, or a complex place. And then this V turns out to be, if you like, it's the pair sigma and C sigma from K. Well, you see now this is not. You see it's not a map now, it's two maps. Where K, sigma goes from K to the complexes, and the image of sigma is not in the, image of sigma doesn't lie in the reals. So there's an infinite place. So that's what's going to be going on at infinity with our Adele ring. So let me just define the infinite place first. Right? Let's define. That was a nice piece of chalk. Oh, it was less nice than I thought. This looks nice. Let's define K infinity to be the product. So this is V infinite. So I better say what KV is, where if V is real, then KV is just the reals, right? And it contains K via sigma, right? So KV always has a copy of KV always has a copy of K in, and if V is complex, then KV is isomorphic to the complexes. And then sigma is just going to be, let's say, I don't know, and let's say, let's have K sigma KV. If I make this, well, yeah, what the heck? Like just sigma, if you like. I like thinking about these things. KV is a slightly weird thing in the complex plane. KV is isomorphic to the complexes, but there's two isomorphisms, and I'll tell you the names of the two isomorphisms. One of the isomorphisms is called sigma, and one is called C sigma. And I don't, this is, I'm not entirely sure that this is I don't know. Sometimes I find that thinking about things in exactly the correct degree of abstract nonsense generality is helpful. When I was your age, I never cared about this. When I wrote that paper with Toby G, I suddenly realised I had to start thinking about this in a very formal way. So if you like, here's what you do. V goes with sigma and K sigma. Sigma and C sigma. Just fix the sigma. Just choose sigma, right? And then just KV is equal to C. If you like. So V, choose sigma, whatever, KV. KV equals C, and sigma from K into KV. Right? There you go. That's what's going on. But of course, your friend might have chosen C sigma instead, but that's okay, because the two pictures are isomorphic, right? That's what I'm saying. There you go. Making infinite places look far more difficult than they actually are. Wrestling with my own inner angels or something. So there we go. So there's K infinity. So remark is that K infinity is actually just K tensor. There's actually a really cool way of thinking about it. I had to spend quite some time thinking about that sort of thing once. So there you go, that's what it is. K infinity is, this is I don't know. But what's for sure is that K infinity is certainly isomorphic to R to the power of, what would they call it, R1 cross C to the power of R2, right? That's for sure. Although, as I say, the isomorphism is, you can tell I'm slightly concerned about, when I stop writing equals and start writing isomorphic, you can tell I'm worried. So yeah, there's a non-canonical isomorphism because at some point I had a pair, sigma and C sigma, and I had to choose one of them. Blah, 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 blah. So note them. So that's going to be the infinite component of the adels, but we're going to talk about idels, so I just need to analyse the units of this for a minute. It's a ring, right? This is a perfectly good ring, right? And I don't care about the non-canonical business, right? Because if you've got a way of adding and multiplying complex numbers together, and you turn your back, and I secretly replace every complex number by its complex conjugate, and you turn around again, you won't notice, right? Because addition and multiplication commute with complex conjugation. So this is certainly a ring. I mean, that's a ring, and they're the same, right? So note that, let me just talk about the units of this ring. K infinity star. This is a kind of a geometric object, right? This is isomorphic to R star to the power of R1 cross C star to the power of R2. And now C star is connected, right? Because it's two-dimensional, then I remove a point, but it remains connected. But R star is no longer connected. I remove a point, it falls into two pieces. So this is not connected in general. It's not in general connected. Okay, and so what we see is that K infinity star, the connected component, is just isomorphic to the positive reals to the power R1 cross C star to the R2. It's just kind of a handy thing to know. There we go. So what's coming? It's time to stop. But what's coming is the adels of K, right? Equals some kind of restricted product over P of Kp multiplied by K infinity. So I need to explain what, obviously I'm going to stop, so I'm not going to do this now. But this is what we're getting to. This is not a full product. There's something else going on, and there's some issue with the topology as well. But at least I've kind of very carefully written down this infinite place. So this is going to be a topological ring. It's gigantically huge, looks a bit terrifying, but it will turn out that we can work with it. The idels are the units in this ring. It's locally compact. It's got an explicit compact subspace. We're going to see class groups and unit groups. By the end of the next lecture, this will hopefully not be scary at all. I'm claiming that review is going on 4 till 5, but review might also include a little, a glimpse of what's to come, just to kind of prepare you for the topology on the adels. Terrific. So slowly all the pieces are coming together, and maybe in the next lecture I'm going to be able to make some vague global Langlands type conjectures that were all complete nonsense.